All right, example 3 says consider the reaction. So we have 2 sulfur dioxide, SO2 gas, plus 1 oxygen, O2 gas, and it yields 2 sulfur trioxide, SO3 gas. There's 4 ways we can approach solving delta H. Delta H is the enthalpy of the reaction. It's just the energy or the heat released from it. The first way is experimental approach to determining delta H of the reaction. The second way is products versus reactants, or products minus reactants, I should say. The third way is Hess's law. And then the fourth and final way is the bond energy approach. And so we're going to go ahead and take that exact same problem over and over, and we're going to solve it 4 different ways, depending on what type of information they give us. So for the first way, the experimental approach, this is probably the easiest one. For this one, we're going to have delta H of our reaction, and it's always going to be Q divided by the moles of the reaction. So this is probably the easiest way. You just get your energy, your heat, your Q, divided by the moles of the reaction. So first, they give us 9.7 gram sample of SO2, reacts with excess oxygen. And so we know that oxygen is excess, SO2 is the limiting reactant. It releases 15 kilojoules of energy, and wants us to calculate that delta H, the enthalpy. And so our 15 kilojoules of energy, that can go plug on the top right here. It says that it's releasing, so it needs to be negative 15 kilojoules. So make sure you plug in negative 15 instead of positive 15, because it's releasing it, and when you're releasing it, you're letting it go, it's XO, you're coming out. For the moles of the reaction, we have grams, we can convert that into moles. And so that's just a simple step. So we have moles of a reaction, right? So we're going to solve for that and plug it into the bottom part. We have 9.71 grams of SO2. The molar mass of SO2 is around 64.07 for every 1 mole. All right, we need to find the moles of the reaction, not the moles of SO2. And so remember from last semester, there's 2 moles of SO2 for every 1 reaction. So we need to make that conversion. So we're going to continue on just a little bit further. So we have 2 moles of SO2, because there's 2 of them within the equation, in the reaction, for every 1 mole of the entire reaction, right? There's 2 for every 1 reaction. So when we divide all of that out into our calculator, we can plug that into the bottom part right there. So that's the only little tidbit. Make sure you plug in moles of the reaction, not moles of the compound. All right, when you divide those 2 out, you should end up with an answer that is negative, because we have negative 15 kilojoules, and it should divide out to negative 198 kilojoules per mole. All right, make sure you get that. Write a question if you mess something up. Right, moving down to the second approach, it's the products minus reactants approach. Using the delta H from part A, so we need that information, the negative 198 kilojoules per mole. So we need to use that information in part A. Determine the value of the delta H of formation, right? So we need to figure out what the delta H of formation is for SO2. And it gives us the delta H for SO3 is negative 396 kilojoules per mole. And so for this one, it's products minus reactants. So if we have delta H of the reaction, we can get the sum of the products, so delta H of formation of the products, minus the sum of the delta H of formation of the reactants. So F stands for formation, right? And we can get the product formations, sum those together, subtract it from the sum of the reactant formations. And once we do that, we get the overall total enthalpy of the reaction. And so for the first part, we have to multiply and also multiply it, make sure you're multiplying it by the moles as well. I'm just going to move this down a little bit so you can still see the equation from up above. And so we have one product, we have SO3, and we have 2 moles of SO3. So we need to do 2 moles of SO3 times the delta HF, so the formation of SO3, and they gave that to us. It's negative 396 kilojoules per mole. And so our moles cancel out, right? Because two moles, this is kilojoules per mole. So our moles will cancel out. Right, and that is just the one product. So we're going to subtract the sum of the reactants. And on the reactant side, we have SO2 and we have O2. Right, and so our SO2, that's what we're solving for, and there's two of them. So I'm going to put 2x because we're solving for SO2. And we have one oxygen. And if you remember from your table of enthalpies, you should still have it. It's online if you've misplaced yours. Anytime you have a state of matter that is in its elemental standard state, meaning that oxygen is usually diatomic and it's usually a gas at standard room temperature, it's going to be 0. And so whenever you have something in its standard state, it will be 0. So oxygen is just 0. So that kind of cancels out. Right, and we're solving for the SO2, and it said to use delta H of reaction from up above. So our delta H of reaction from part A was negative 198 kilojoules per mole. All right, from here is a simple two-step equation, right? 2 times negative 396. Take it to the other side by doing the opposite, right? So add it to the other side, and then divide both sides by negative 2 to solve for your x. And our x right here, in this case, was delta H of formation of SO2. That's our x, right? And so once you multiply, subtract, add, divide all of that stuff out together, you end up with a delta H, an enthalpy of formation for SO2 that is negative 297 kilojoules per mole. So products minus reactants. Pause here. If you have a question, write it down. All right, moving on to Hess's law. Hess's law is pretty similar. We need to get the overall equation by flipping around the equations. For this one, we need to make it into the overall equation from up above, and our overall equation from up above was 2 SO2 plus 1 oxygen, and it made 2 SO3. Right, so we need these three to become that one equation. And so the way I look at this is I look at what's on which side. Do I need to flip it first, and then do I need to multiply or divide by a certain number? So the first one, we have SO2, right? I see SO2 right there. And we have SO2 in our other equation. So I know that right away it's on the right side. I need it to be on the left side, so I'm going to reverse that equation. So I'm going to reverse the first one. And put 2H2O plus 2SO2, and then 2H2S plus 3 oxygens. So I reversed the first one right there. If I look at the second one, I have SO3 on the left, but SO3 needs to be on the right, and there's only one of them, and I need 2 of them. So I'm going to reverse the second one and multiply it by 2. Right, so I'm going to reverse it and multiply it by 2. So then I end up with 2H2SO4, 2 waters, and 2 SO3s. All right. The last equation, I have oxygen, and I have 2 oxygens, right? And I have 1 oxygen here. If I look through, though, I also had oxygen right here. And there was 3 of them, so I need to actually multiply this one by 2 because I need 4 minus 3 to get 1 oxygen. So I'm going to keep this one, but I'm going to multiply it by 2. Oops, there we go. So I'm going to multiply the third equation by 2. So we have H2S plus, so 2 of them because we multiply it by 2. 2 times 2 is 4 oxygens, and then we have 2H2SO4. All right. If we did this correctly, we add up all of them, we can see that the left and the right side will cancel out, and we should end up with the overall same equation as the beginning one. That's the one that we wanted, right? So we're going to look at what's the same on the left and the right, cross it out if we can. So we have 2 waters here, and we have 2 waters here, so we can cross those out. We have 2 SO2 on the left. There's no SO2s on the right, so that one's okay. We have 2 H2S, and we have 2 H2S, so we can cross those out. We have 3 oxygens and 4 oxygens, so we can cross out 3 of them, and this reduces down to 1. which is perfect because we wanted 1 oxygen. We have 2 H2SO4. We have 2 H2SO4 on the right, so we can cross those out. And then we have 2 SO3s. So that one is good because that's how much we wanted. Right, and so we did this one correctly. We can rewrite the equation. It's the exact same as the one above. We're going to do the same thing with the delta H's. So we're going to do the same thing that we did with the equations to the numbers. So I'm going to scroll this one down a little bit to give me some more room. Right, and so for the first one, the first delta H, we reversed it. So when you reverse it, you just make it positive. So instead of negative, it's going to be positive 1,124 kilojoules per mole. The second equation, we reversed it and we multiplied it by 2. So that one's going to be positive 2 times 132, so that's 264 kilojoules per mole. And for the third one, we didn't reverse it, so it's still negative, and we just multiplied it by 2. So 2 times 793 should give us 1,586 kilojoules per mole. The last part was just adding them all together, so when you add all 3 of those together, you end up with negative 198 kilojoules per mole, which is perfect because if we look up at A, there it is, it was negative 198 kilojoules per mole, which means we did this one correctly.